in developing inferences about the slope parameter beta 1, we start with the properties of the sampling distribution of beta 1. And what we will tell you but won't show you or prove to you is that the expected value of this is equal to the true population parameter. So that makes our estimator an unbiased estimator. And then our standard deviation of beta 1 is going to be equal to our standard error divided by the square root of capital S sub xx, right? And what's going to happen there is that we don't know that value, and so we'll estimate that by substituting in S sub e, standard deviation of the error, divided by the square root of capital S sub xx. Right? And then beta 1 is going to be normal distributed, and of course that's because we assume that our error terms were assumed normal way back at the very beginning. So this is not an assumption so long as the error terms are actually normal from the very beginning. Right? Those three things right there will allow us then to come and develop confidence intervals for our slope term and hypothesis tests for the slope term in a fairly straightforward fashion. And when we make this estimation here, that's going to lead us to the t-distribution. Right? And so for the data that we've been working with in the previous examples, we're going to go for a 95% confidence interval, two-sided, and the statistic that we're going to use then is that t is equal to beta 1 hat minus beta 1 over S sub beta 1. This guy right up here is our S sub beta 1. Okay. And from our earlier work, our measured beta 1 was 0.9047, and our standard deviation for beta 1 then is going to be 0.912. That's the standard deviation of those residuals, divided by the square root of capital S sub xx, which is 79.1, and that gives us 0.1025. Okay, so the t value that we go and calculate here are 95% two-sided. Right, so that leaves us 0.025 out in that tail. We have, oh wait a minute, how many degrees of freedom? Now we're down to n minus 2 degrees of freedom. So t sub 0.025, right hand tail area of 2.5%. Degrees of freedom being 15 gives us a t value of 2.131. Okay, so our confidence interval then is going to be our measured beta 1 value plus or minus our t value that goes along with our confidence interval, right? So in this case 0.025 comma 15 times our standard deviation. Right, so that will be then 0.9047 plus or minus 2.131 times 0.1025. And that's going to lead us to a confidence interval ultimately that is got a lower bound of 0.6862 and an upper bound of 1.1232. And note that it contains the value of 1. The reason why that's important in this case is because remember this data was about discharge and recharge of an aquifer. And so the recharge was the independent variable and the dependent was the discharge. And so having this slope parameter of 1 suggests that we have sort of a preservation of volume of our water resource. Right? That what is going in is what is coming out. And that's what essentially this particular slope value is telling us. And so when we come down here for the hypothesis test for beta 1, then we naturally might think about then that our null hypothesis is that beta 1 is equal to, and I'll substitute in here the symbol from your text, beta 1 comma 0. It's beta 1 is the null hypothesis. That's where the second subscript is coming from. And that is equal to 1 in this particular case. We'll do a second hypothesis test where we'll change that value. The alternative is going to be a two-sided that it's not equal to 1. Right? And so the test statistic that we're going to look at is once again the t in that nomenclature from the text, beta hat minus beta 1 comma 0, and in the denominator I'm just going to directly put our standard deviation that we're working with for that parameter. Right? And so for our calculated value, we'll have 0.9042 minus 1 divided by 0.1025, and that will give us a t-value of negative 0.9346. And if you go look up the p-value, well, you'll have a little bit of a hard time if you use the Montgomery and Runger tables. There are other ones that are out there, or you can get them straight from the software program. And in this case, remember, it's a two-sided, so depending on what your table you're looking up, you may have to double this. And this is going to be on the order of 36%. Right? So we're actually pretty close. What this is telling us is that there's a pretty good strong likelihood that just the natural variability will explain why we're not exactly equal to 1. And so we have no reason to reject the null hypothesis. And we see that too if we come down and take our significance level of, say, 0.05. It's two-sided. That will also lead us to a t-value of 0.025 and 15 degrees of freedom. We know that's 2.131. So our test statistic, when we look at the absolute value, is less than our t critical value. So therefore, do not reject the null hypothesis. Right? Makes sense. We saw a fairly strongly linear relationship, and the interpretation of physically what's going on in the system says that water in equals water out, no change in the storage of any significance here. Right, now, that's one null hypothesis that we might have looked at. Let's look at a second case, and a very common one, and that might be to ask the question that our slope parameter ought to be 0, right? Meaning that there's no linear relationship between our two variables. And so that's kind of a good one to also take a look at. Our calculated t-value then changes 0.9042 minus 0 over 0.1025, and that now gives us a t-value of 8.82, which is a p-value that is 2 times 10 to the minus 7th, right? Or you can look at it and say 8.82, that is larger than 2.31, and so therefore you reject this new null hypothesis, right, that beta 1 is equal to 0. That also makes sense. Both of them are consistent. That we do expect some form of a relationship that's happening between the recharge of the aquifer and the discharge of the aquifer.